Hello everyone, welcome back. This video is on the extended Euclidean algorithm. We start with the following statement. Let's let a and b be integers, not both 0. A linear combination of a and b is a sum of a multiple of a and a multiple of b. So when you have a multiple of a plus a multiple of b, that's what we call a linear combination of a and b. So this theorem states that the GCD of a and b can be expressed as a linear combination of a and b, and in fact the GCD of a and b can be expressed as the smallest positive linear combination of a and b. So among all the linear combinations of a and b, the smallest positive one is equal to the GCD. Here's an example. So the GCD of 246 and 194 can be checked, that is 2, and one can easily check that 2 can be expressed as 52 times 194 minus 41 times 246. So here we are writing the GCD2 as a linear combination of 194 and 246, and the value of m and n here are 52 and negative 41. So now let's try to prove this statement. So let's let I be the set of all integers x such that x is a multiple of a plus a multiple of b. Then I is clearly non-empty because in particular a and b are in I. And you can easily check that I is closed under addition and subtraction, because if you add two linear combinations of a and b, you end up with a linear combination of a and b. If you subtract two linear combinations of a and b, you just end up with another linear combination of a and b. So I is closed under addition and subtraction. Now, because it is closed under addition and subtraction, and I is simply a subset of the integers, we can apply the z-ideal lemma that we have seen before. And by the z-ideal lemma, I contains a smallest positive integer d, and every element of I is a multiple of d. So since d is in I, obviously d would be a linear combination of a and b. So because d is in I, we know that there are integers m and n such that d would be ma plus nb. And so the remaining, what remains to show is that d is indeed the GCD of a and b. So once we show that d is the GCD of a and b, then we will be finishing the proof. So this I left as an exercise for you to show that d is the GCD of a and b. The question now is, so in this example, when I told you that the GCD is 2, and then here is where we express the GCD as a linear combination of the two numbers 246 and 194. But how did I come up with 52 and negative 41? Well, so recall the example that we did when we found the GCD of 162 and 31. We applied the Euclidean algorithm, right? So we said, okay, 162, I want to find the GCD of 162 and 31. I divide 162 by 31, and then I get a remainder of 7. And then I divide 31 by 7, I get a remainder of 3. and then I divide 7 by 3, then I get a remainder of 1, and then I divide 3 by 1, then I get a remainder of 0. So as soon as I get a remainder of 0, I stop, and I know that 1 would be the GCD of 162 and 31. So let's now see how we can use this to express the GCD 1 as a multiple of 162 plus a multiple of 31. Well, the way we do it is from the very first equation, we see that we can solve for 7, and 7 would be 162 plus 31 times -5. So we can solve for 7 in this way. And then in the second equation, we can solve for the next remainder 3. And the next remainder 3 is 31 plus 7 times -4. Now, in place of 7 here, we can put the expression 162 times 1 plus 31 times -5. So we can replace 7 by 162 plus 31 times -5, and then we can simplify that, and then we can express this in terms of 162 and 31 again. So the 3 can be expressed as 162 times -4 plus 31 times 21. So what I'm trying to do is, at each step, each remainder, I'm expressing that in terms of 162 and 31. Next remainder is 1. We can solve for 1, and we get 7 plus 3 times -2. So now I can replace 7 from the first line, and then I can replace 3 from the second line here. So 7 would be replaced by this, and then 3 will be replaced by this. So if I do that, if I replace 7 and 3 here, then I can again express 1 as a multiple of 162 plus a multiple of 31. And so there you go. We have found that the GCD 1, we can express that, the GCD 1, we can express that as a multiple of 162 plus a multiple of 31. Okay, so that's basically the idea behind the extended Euclidean algorithm that I'm going to present now in a more in a tabular form. So here's so let's say I want to find the I want to express the GCD of 246 and 194 as a linear combination of the two numbers. So how do I do it? So that is, in other words, as I told you already, that the GCD of these two numbers is 2, and then we can express 2 as 52 times 194 minus 41 times 246. The question is, how do I come up with 52 and -41? So we create a table. The first column, we write the remainders. The second column, we write the quotients. In the third column, we are creating, so we are basically, if you remember this calculation that we did, we kept updating, or we kept expressing the new remainder in terms of the two original numbers. So these are so as you do that, as you express each remainder as a linear combination of the original numbers, what are the coefficients there, right? So S and T, so S is here, they keep track of the coefficients of the first number 246, and the T's they update the coefficients for 194. So in the initial setup is as you always write the bigger number 246 first, and then the smaller number. Quotient for at the beginning would be empty, and then you start with the initial value for S would be 1, 0, and then for T would be 0, 1. Okay, so the next step is that you divide 246 by 194, and then you update the quotient and the remainder. So if I divide 246 by 194, the quotient would be 1, the remainder would be 52. Now how do I update the S value? Well, the S value would be, you have to go two values back, and then you get this 1 minus, so you multiply 0 and the quotient here, so 0 times 1, and you subtract that from 1, and that's going to give you 1. Similarly, you multiply the quotient 1 with the 1 here, and then you subtract from 0, so that's going to give you -1. Okay, so now we do this, we divide 194 by 52, and if we do that, the quotient we get is 3, the remainder that we get is 38. And so now we update the S value again, so we just go back two values back, and now we multiply the immediate past value of S1 with the quotient 3, so that's going to be 3, and then we subtract that from the previous S value, so that's going to be 0 minus 3, which would be -3. We do the same thing here, so we multiply -1 and 3, which will be -3, subtract from 1, we get +4. Okay, we just keep doing that until we get a remainder of 0. So now we divide 52 by 38. That's going to give me a quotient of 1, remainder of 14. And then again, to find the S value, I go back 2 places. So -3 times 1 is -3. Subtracting from 1 would be 4. 4 times 1 would be 4. Subtracted from -1 would be -5. Okay, now you divide 38 by 14, you get a remainder of 10, quotient of 2. Again, you update the values of S and T. So you keep doing that until you get a remainder of 0. When you get a remainder of 0, you stop and notice that, and look at the last step before you got the remainder 0. And then the S value here would be -41, and the T value here is 52. So the S value would be the coefficient of 246, the first number here, and then 52 would be the coefficient of 194 here. So you can see -41 would be multiplied by 246, 52 would be multiplied by 194, and then if you calculate that as what that is, that's exactly the GCD2. And we know that the remainder 2 here is the GCD by the Euclidean algorithm. So that's how we can express the GCD of two numbers as a linear combination of the two numbers. Okay, so here's the set of exercises, and where you have to apply the tabular form of the algorithm. Okay, so that's it on the extended Euclidean algorithm. We're going to be using that a lot later, and the next time we will start talking about prime numbers. See you then. Hello everyone, welcome back. The topic in this video is the Euclidean algorithm. This is an algorithm to find the GCD of two integers. So here we'll be talking about finding the GCD of the integers a and b. And first of all, I'm going to start with two facts here. So let's let a, b, n, r, and k be integers. And let a be equal to bq plus r, and this is by you can think of this by the division algorithm. So if you divide a by b, q is the quotient, r is the remainder. Now if k is a divisor of any two of the three numbers a, b, r, then k is also a divisor of the third number. So in other words, what I'm saying here is that if k divides a and b, then k also divides b and r. Or you can say if k divides r and a, then k divides b as well. So if k divides any two of the three numbers a, b, r, then it divides the third. Another fact is that if you have the equation a is equal to bq plus r, then the GCD of a and b is the same as the GCD of b and r. Now the good thing about this, the implication of this theorem is that you see, if you start with a and b and you're trying to find, let's say b is less than a, you're trying to find the GCD of a and b. Now because the GCD of a and b is the same as the GCD of b and r, so you just have reduced the size of your problem because r is less than b. So if you started with the pair, if you wanted to find the GCD of a and b, you can find that by just finding the GCD of b and r, and the size of b and r would be less than the size of a and b. Now these two facts follow by just looking at the equations a is equal to bq plus r, which is the same as r is equal to a minus bq. So notice that so why would they, why is it that well, first of all, let's look at the first theorem here. So if you say that k divides, so notice that if you look at the first equation, if k divides b and r, then then k divides the right hand side, and then k divides a. So if k divides b and r, then k must divide a. Now if you look at the second equation, if k divides a and b, then k must divide r. So now notice that if k divides a and b, right? If k divides a and b, any common divisor of a and b will also be a divisor of r. So and any common divisor of b and r will be a divisor of a as well. So that tells you that the GCD of a and b and GCD of b and r would be the same. So we're going to make use of this in the Euclidean algorithm. So let's say we want to find the GCD of two integers a and b, and I'm going to label them as r0 and r1. The next step would be that we divide r0 by r1 by using the division algorithm. So r0 would be r1 times the quotient q1 plus the remainder r2. Obviously r2 is strictly less than r1. Now we divide r1 by r2, and if I divide r1 by r2, then I'm going to get a quotient q2 and the remainder r3, and r3 is strictly less than r2. And if we keep going like this, and then at some point, let's say on the kth step, rk minus 1 would be rk times qk plus rk plus 1. And let's assume that the values of these r's, right, r1, r2, r3, and so on, these are non-negative integers, and they are strictly decreasing. So at some point rk plus 1 must become 0. So at some point, so let's say rk plus 1 0, and then what happens is that you can say that rk is the GCD of a and b. So why is that the case? Well, if rk plus 1 is 0, then what is the GCD of rk? See, the GCD of rk and rk plus 1. Well, if rk plus 1 is 0, the GCD of rk and rk plus 1 would be rk. But the GCD of rk and rk plus 1 is the same as the GCD of rk and rk minus 1. So the GCD of these two and the GCD of these two are the same. So you can say that the GCD of RK minus 1 and RK would be RK. And then you go backward, and in each of the steps backward, you'll see that RK would be the GCD. So, so if you say that R2 and R3, the GCD is RK, then the GCD of R1 and R2 would be RK. And then if the GCD of R1 and R2 is RK, then the GCD of R0 and R1 would be RK. And so that's what you wanted to find. So the point is, if we keep using the division algorithm like this, as soon as we got the remainder 0, the previous non-zero remainder would be the GCD. So let me explain that in an example now. Let's say I want to find the GCD of 24 and 18. I start with 24. So you divide 24 by 18. Then you get a quotient 1 and a remainder 6. Okay, so now we divide 18 by the new remainder 6. So we get 18 is equal to 6 times 3 plus 0. So we got a remainder 0 already, so we stop. And the GCD would be the previous remainder that we got, which is 6. So the reason is, again, if you look at the second equation, the GCD of 6 and 0 is 6. But the GCD of 6 and 0 is the same as the GCD of 6 and 18. So the GCD of 6 and 18 would be 6. Now GCD of 6 and 18 is 6. So then GCD of 18 and 24 would be also 6. Okay, so that's how we get this GCD 6. Here's another example. Let's say I want to find the GCD of 162 and 31. So I start with dividing 162 by 31, and that's going to give me a remainder 7. And then I divide 31 by 7, that gives me a remainder of 3. And then I divide 7 by 3, that's going to give me a remainder of 1. And then I divide 3 by remainder 1, and that's going to give me a remainder of 0. So once I get the remainder 0, then I stop, and the previous remainder is my GCD. The reason is the following. So if I say that the GCD so the last equation tells me that the GCD of 3 and GCD of 1 and 0 is 1, but the GCD of 1 and 0 is the same as the GCD of 1 and 3. So that's 1. GCD of 1 and 3 is 1. So GCD of 3 and 7 would be 1. GCD of 3 and 7 is 1. So GCD of 7 and 31 would be 1. GCD of 7 and 31 is 1. So the GCD of 31 and 162 would be 1. So that's how we get 1. So basically we are applying this second theorem here repeatedly to get to the GCD. Okay, so here are some exercises that you should go over before you move on to the next slides. And the next video will be going over the extended Euclidean algorithm. See you then.